All right. Hello, everyone. Welcome back. So before I start today's class, some of you didn't choose a group yet. So I assigned you randomly to each other because you're procrastinator. So I thought you should be grouped with each other. I didn't want to mess up with others that they had their plans. So you know who you are. I know who you are. It's gonna be interesting. Make sure you're not in two groups. So I use my enrollment list to divide graduate student and undergraduate student. Some of our graduate students are in undergraduate student or in graduate program. So if I grouped you wrong, let me know. If you group yourself in another group and I put you in a different one, that might happen. Also, please let me know today. All right. So today, all the groups have to be finalized. Contact your team members. Everybody is responsible for the final product that comes out of this assignment. So if someone does part one, someone does part two, and part two doesn't look good, both of you will be penalized, right? So because it's both of your jobs to check each other's work. Part one is easier. You have part of the solution as exam one. The other part is just a matrix that you need to grab from lecture slide, code it, and run through a for loop or something. So it's not difficult, right? So part one should be quick. Part two needs some brainstorming. You have different way of approaching it. You could approach it completely graphically, you know, like graphical methods, not other graphically. Sine, cosine, points. I know the length of my link. I'm gonna move everything 1 degree and I'm gonna just do 1 degree. It's fine. You can use the rotation, the transformation matrix for every link, and you have the position in the last column. You can grab that, plot your point, find your point, plot a line, connect. So that's your next frame, right? You could do that. So I'll put it up to you. Make sure, so use lines for links, use objects like circles, stars, something that's visible for your joint. So I know where the joint is and where the link starts. There are two ways of showing this motion. You could say, okay, I have 4 different joints. Let's say joint 1 is 45 degrees from U0, from your default value. Then next one is 35, -10, 1 meter. You could say, okay, let's move everything 45, show the motion, create some pauses so this motion is visible, right? I can see it. Then you can go to the next joint, move it, third one, move it, and fourth one. So every joint moves separately. That's one way to look at it. Way 2, start. So you divide the input, let's say to increment like 100 increments, right? So let's say it becomes 2 degrees on one degree on the other one. So you have to just divide. Then at so next iteration, from iteration 0, in iteration 1, everything moves 1 degree, right? So the whole robot will move 1 degree, everything, and maybe 0.1 meter. Then iteration 2, from that position, another degree, right? So that will create a smoother path. Still, you can see the motion. These two look different when you run the simulation, but the end product, the position of your end effector will be the same. All right, I'll leave it up to you, whichever is easier for you. Point number 3, the position of end effector that you will find from your simulation should be comparable to what you find from analytical solution, part 1. Now, why I say comparable, not exact, because some of you might add some structural element to your simulation to might just make it look better, nicer. To have it elevated from the ground, right? To put your frame 0 and frame 1. Maybe you want to give some length to your prismatic joint, like the part that is fixed and doesn't move. So that adds some distance that has to be counted in. So when you look at the two matrices, they should be explainable if there is a difference. And it reflects back to the structure of your robot, how you designed it. All right. So write 1 or 2 sentences that compare these values. And if they're the same, good to go. If not, why do you think it's different? There might be some of these cases that happens. Make sense? I cannot emphasize that how much important it is to work on part 2, part B together. So it will be faster. All right. Do not use any tools. You can videotape the whole thing with your phone, or you can use your Windows screen, right? And then if your file is too big, don't submit through Carmen. Upload it on OneDrive. Send the link as part of your submission. So everything goes through, especially that if you haven't submitted yet, your plan is to submit like on Wednesday, right? And whenever the deadline is. And the submission might not go through because everyone's trying to do the same thing, right? So don't break the system, don't break it. So count all of this. Do not submit zip file. Okay, you probably will get 0 or angry email from Brett because he has to go through every single file you sent. It's better they're all separated. Sounds good? Awesome. Okay, so last class, we ended our example, and then it was kind of rushed, and then I explained singularity. So I'm gonna explain singularity again today, hopefully if you have time. And I'm gonna review last class example, and there was a typo. I'm gonna show you what it is. I think 7 was trying to tell me and I didn't listen, so my bad. But let's go and review. So this way we can review what happened on, well, on Friday. Stop broadcasting. All right, this example. I realized this when I was going through the submissions for CP13. I saw some of, like most of you calculated the way I did, which was one part of it was wrong. So when I calculated V3, this one, so this didn't translate to final solution. Final solution is correct. This one was wrong because there was L1 plus cosine theta 1 here. That is wrong. So now I'm going to explain it to you. So there are two things. Let's once for all solve this problem. I'm from frame 0. How do I go from 1, frame 2, right? So this doesn't have anything to do with this example, just in general. So let's say home position of a 2-hour robot. We're going to say home position, everything 0, right? Now, I'm going to show you how to move them separately. You can also use this for your code. So let's move your first joint theta 1 degree. We are not moving to in the second joint yet, right? So the link connect to second joint is not moving. So when I move the first joint theta 1, L1 is moving. So the base of this frame, which is at the end of, so frame 2 is at the end of L1, right? So when I move theta 1, this whole rotates theta 1 degree. The position, if you want to calculate this, in base seen from base frame is going to be L1 cosine of theta 1 for X and L1 sine of theta 1 for Y, and Z is 0, right? Now, let's rotate the second joint. I rotated theta 2. So this theta 2, you see that since this wasn't moved, here is still in 0 position. So going theta 2, you're moving from here, right? So I moved some angle. I moved it here. So the frame is moving. Your robot can also be following the same path when you're showing the simulation motion. Does that make sense? You could show them separately. But the idea is now, if I want to know where this point is, there are two things. I either can express the length from frame 0, which will be this whole length, right? For X and Y, that's one way, correct? That will be positioned in frame 0. Agreed? So now for the previous example, for example in velocity propagation, if you remember, propagation is when we go from one frame to another, right? So if I'm on frame 1 and I'm going to this frame, I want to find PE. PE moved because L2, which is connected to the second joint, moved, right? Now, if I want to find PE as seen in frame one, not expressed in frame, sorry, as seen in frame zero, not expressed in frame zero, is L2 this length, right? Because that's how much it moved, correct? So the calculation is happening from here. Times, so frame zero sees a theta one because the previous frame moved, and a theta two because the second frame moved. But when I'm writing PE for velocity propagation is with respect to the previous frame, is not with respect to base frame. You just consider all the rotations, because from this frame, you see that L2 moved theta 2, but you also have already experienced a theta 1, right? So this is the part that at the end, I think someone from the audience said L1 cosine. I said yes, and then I wrote it. I won't call who, I remember who it was. But so it was my mistake that I didn't catch it. So in velocity propagation, when you're calculating the positions, it's the position from the previous frame, right? You just consider the thetas because the frame itself rotated. That's why we consider that theta. That's why that becomes L2 cosine of theta 1, theta 2, which I wrote it as L1 cosine theta 1, 2, which is theta 1 plus theta 2. Hence, this is the correction. It is considered already in this. So the final solution was correct. Now, I know a lot of you, when you did CP13, followed the L1 plus cosine theta 1. So you wrote express the point in frame zero. It's fine. Everybody will get their point. It was basically my mistake. I will post the solution to P13. You can go over, and if you have problem, we can discuss and explain it more. All right. So there's a little bit of different way of looking at this, expressing it in a frame and just seeing it, what is happening from a different frame. You just have to consider this for the velocity propagation method only, because we are jumping from one frame to another frame. Okay. Yes. Is there a zero below? Oh, there's a zero. I didn't put the zero when I corrected. Yes. So the z value is 0. Thank you. Yeah. Otherwise, it wouldn't make sense. Thank you. All right. So hopefully this will help a little, and then this part will help you also with your simulation and in general how the robot moves. All right, so that was it. Now go back to this lecture. All right, so we covered direct method for calculating Jacobians. We covered velocity propagation, which we call implicit method. We also have a method called explicit form or explicit method. You're going to use the knowledge we have previously to create that, especially when you have the transformation matrices between the frame, or you have the POE already calculated. It's easier to use explicit method because you have all the information available. You just have to pick them and put them in place. All right. So let's say we are in frame I and we want to calculate the Jacobian in frame, the end effector frame. All right. So I'm just going to say that here, this frame itself, if you put it in the last frame, could have a velocity and a rotation, right? Like angular velocity and linear velocity. So Vj. Now, if this was your frame N, so you're in frame I, the distance between these two is Pi to N. So I picked two random frames, so you can even calculate it to that Vj. So this just means there is a prismatic joint somewhere before that, and there is a bunch of revolute joints before that. So you have both elements available. So we basically in this method kind of resonate with velocity propagation. We want to see what's the contribution of each joint velocity on the end, which is basically your velocity kinematic, right? So you're gonna say, if we have a prismatic joint, if we have a revolute joint, what's gonna happen to linear velocity and angular velocity? So linear velocity, if we have prismatic joint, That's Vj, right? Whatever linear velocity we have before it. So we say that Vj would be our velocity because of prismatic joint. At that frame n, what kind of velocity we could have if we had revolute? So these are all reviews, right? We already know all of this. So omega I cross product of p, the distance between the two frames. Now, if we have angular velocity, if you want to calculate angular velocity, what's the effect or contribution of prismatic joint to angular velocity? 0, right? So these zeros are important because when we are writing a Jacobian, they're all zeros, 0 columns. So you need to understand, you need to look at your robot. If you see prismatic joint, you know, they don't contribute to the angular part of your Jacobian. And what's the effect of contribution of angular velocity if you have a revolute joint? Whatever angular velocity that joint has, right? Its own effect. So this is just basically what we knew before, but we're kind of dividing in linear velocity, angular velocity. You saw that J could be divided into segments, JV and J omega. So all of these, if you want to put all the linear velocities together, the linear velocity of the end effector is due to combination of all the linear velocities because of your prismatic joints, right? Because we're checking the effect of each joint on our end effector. So all the linear velocities plus the linear effect of our revolute joint on the end effector. Now, what's epsilon here? So so this is kind of written as like a pseudocode, an algorithm. So just to help you to write, just condense them. So epsilon is 1 if you have prismatic joint. Epsilon is 0 if you have revolute. Now, if you look at here, so if you have prismatic joint, VI, whatever it is, will be counted, right? Now, if the joint was revolute, your epsilon is 0, right? So this becomes 0 times VI, so there is no linear velocity because of that revolute on that frame itself, right? Now, what is epsilon hat or epsilon naught? Yeah. So this is a neat way of remembering it. Now here, epsilon naught, if you have prismatic, you don't have omega, right? So that becomes 0. And if you have revolute, that becomes 1. So you have the contribution of your revolution. Same for, so now for angular velocity, we only have this omega naught because, no, sigma naught. What is this called? What do you call it? Epsilon, sorry, epsilon naught. So we only will have epsilon naught because we don't have, like, prismatic joints do not contribute in angular velocity, right? So again, these are the repetition of what we have seen so far, but you have put it in a very nice, neat way. So if you remember 2 sentences, that's the 2 sentences you want to remember, knowing what epsilon or epsilon naught is. So if you remember what epsilon is, you know what epsilon naught is. So to write the linear velocities, if you want to open this, so okay, so these are the velocity time qi, q dot I, the effect of each joints, right? However many joints you have. Same for angular velocity. This guy, what is this guy? So if this is part of velocity kinematics, so this is your velocity of a robot, the linear part, is something times the joint velocities for the linear part. What is this segment? Velocity kinematic is Jacobian times each joint velocity, right? Now, we are looking at end effector linear velocity expression. what this could be? This is the linear part of Jacobian. It's not that Jacobian is nonlinear. The part that affects on the linear velocity. What is this part? So the angular velocity of the end effector is equal to something times the velocity of the joint. I know everyone knows it. It's just late in the afternoon, nobody wants to talk. J omega, right? We know that J is JV over J omega. So if we find this, if we expand this, put it here, and if we expand this, put it here, you will have our Jacobian. Now, why this is special? You see that here, the linear velocity, if you have prismatic joint, this is either 0 or 1, right? So it's not really important. If it is prismatic, it's 1, we can't count. What is this? The axis of that prismatic joint, right? So we reduced it to, there's a prismatic joint, find the axis, put it here. That's done. You're done with that part. Plus, if we have a revolute joint previously that will have an effect, you know, create a linear velocity, what do we have to look? Well, this is epsilon naught is just if it is revolute or prismatic. So not very important, but then you have the axis, right? Cross product of the distance. So we reduced it to, so we already know the axis of each frame, right? Each joint. All we have to calculate is what is the distance of our frame to the frame that we are calculating based on. So we reduced everything to frame the joint axes and the distance. Finding that this will be the Jacobian B, the linear. This is super easy. Epsilon naught, 0 or 1. Well, obviously for here it's 1 because it's revolute, right? Only for revolute joint. And the joint axis, right? Now, what if I had, write this, if you had R or P manipulator, write J omega for this. Let's say it is planar. Planar means that all the Z's are coming out of the plane, right? What is the J omega from this method? For J omega, you don't even need to calculate. You can just tell by heart. Anyone? Yeah. Very close. What is the last joint? Prismatic. What's the effect of prismatic? What is epsilon naught? 0, right? See, the second part of Jacobian is super easy. You just need to know which direction is the joint axis. Does this make sense? So for this part, it doesn't even matter what is the configuration of your P. So it's not going to have any effect on the J omega. I'd like you to understand what's happening here before we move on. Let's do another example. If we had, let's see, this is Z1, this is your base frame, X, Y, Z, 0, and then this is Z2, and then this is your P. So this is Z3. This is E2. What's J omega for this scenario? Yes, E2 is also rotation. So this is a E3, theta 2, theta 1. What's J omega? I want everyone to do this. If not, I won't even go to the next part. You can go home and see it. Because this, we have done it so many times. If you can't do this one, there's no point for me to continue. Let's see. Megan, what is the first one? So there's gonna be 3 columns, right? J omega is gonna be 3 by 3. Hopefully you'll know how. So you're gonna have 3 columns. Megan, what's column 1? 0, 1, 0. Agreed? So base frame, we're calculating everything with respect to this. Z-axis in the direction of y, and the other 2, because this is orthogonal, 90 degrees, they're 0. So 0, 1, 0. Next, Ryan. 0, 0, 1. All right. Yes. Yes. Prismatic, right? You don't even think about it. So J omega is the easy part. The cool thing is once we have J omega, this is Z1, Z2, Z3. So we kind of have part of these, right? So we have all the Z axes already. So it's a good idea when you're writing the Euclidean, find J omega first, because there are all the axes, Z1, Z2, Z3, base frame. And all you have to do is find the distance and do some multiplication. Right? Connor, following? All right. So this is basically just the open what we saw in the summation form. So your linear velocity would be epsilon 1 z1 plus epsilon naught z1 cross product p1 and n, right? Because we're trying to find the Jacobian for end effector. So we are going from frame 1, where end effector is. Frame 2, where end effector is. Frame 3, where so your p is changing, right? So does this make sense? So we're trying to find where the position of end effector is as we move through the frames. So JV of JV times Q dot. So Q dot is just our the velocity of each joint. We find JV from here. And omega is super easy. We just did it. Epsilon naught Z1 Q dot 1. So we just have to find Z axis of each joint, and we have J omega. Right? So now, question for you. If I have T2 to 3, let's say end effector is on the 3rd frame, right? Can I find P2 to 3 from this? The position of end effector as seen from frame 2. If you have the transformation. Yeah, how? Yeah. So it will be here, right? So now, when you are solving forward kinematics, if you're using especially DH table, my favorite method, because you have to find every t between frames 0, 1, 1, 2, 2, 3. So you kind of have all the position already available, right? So you just have to, if you need to find, let's say you have T1, 2, and then you have T2, 3, you want to know what is P1, 3, you find T1, 3, multiply these two, and grab the last 3 elements for the position of that, of your frame, with respect to that, the frame that you're looking for, right? So, theory method is a little bit more calculation to do, but you still can do it also. Use it. I usually use DH method because like there is more, it takes more effort to create the table, right? But then you can use it so much in simulation and in calculation all this stuff.
So you can get the position 1, 3, T1, 2, and T3 by multiplying.
So here, let's say you have T1, 2. You have 2, 2, 3.
Can you just add them together or no?
But you don't know if they're planar, yes. But if you're in a different plane, no. Yeah. So if it's planar, you can do that. But you can't. So let's say that you didn't see the robot. I just gave you the matrices, which you'll see the example here. So it's just the best is just follow. It's like, hey, T1, 3, sorry, is T1, 2, T2, 3, and then grab the 3 points from it. Yeah. Okay. So you could, as we talked last time, you can find Jacobian in different frames, right? So if you found in one frame, all you have to do is you use the rotation matrix between the frames to find Jacobian seen from the other frame. So if I write partial of so this is another method. Well, this will resolve the same thing. Okay. Sometimes when you have the transformation matrices, we have all the positions, you can use partial derivative of each of the location with respect to all the string variables to find the linear part of your Jacobian. So the angular part is the same. For linear part, if you didn't have the robot, but you had the transformation matrices, that's one way to do it. It will give you the same thing. Basically, hey, what's the position? What's the effect of each on the position of that frame? And we discussed frame finding Jacobian in frame 0 is called basic Jacobian. I remember what was it called? So it's called basic Jacobian. So what is the Jacobian of the end effector in frame 0? Then you can just multiply it by rotation matrices for different frames. I think I gave you the equations before. So this is basically Z1 in frame 0. Now, example. Let's see, T01. So if you saw that form in any of the example you find online, this is equal to T03. So this is a different notation of, so T03 is T03. Other different notation that different people use. All right, let's say you're given a certain PRP manipulator, but you don't see the configuration, all right? And but you know what the transformation matrices are, and frame E is the frame of the end effector. So here, E and 3 are the same. So they are not the same. Right. We want to derive the basic Jacobian that relates during velocity to end effector linear and angular velocity in frame 0. Right. So since we have the transformation matrices, the best way is to use that partial differential equation that I just showed. So find all the position and then get the derivative with respect to different joint variable. What's the joint variable here? What's Q? So, theta 1, maybe D2, theta 3. if someone says Q is theta 1, theta 2, theta 3 is right, as long as you know this is prismatic. Okay, again, this is like how there's a convention. As long as you follow your own convention and explain what it is, we accept it. But since here they are using D2, like you can check. So I'm gonna call that D2. So it will match the rest of the transformation matrices. Now, what are we trying to find here? Jacobian. So it's asking us to find linear and angular velocity in the frames. To find Jacobian, we know that we can easily find J omega and then find JB after that. So I'm gonna write this. I'm gonna say that, hey, J omega, J is JV, J omega. So I'm gonna find it in two separate sections and then just put them together. All right. What is J omega? So one quick way to find the hat. So you have to look at two things, right? First, the configuration of your robot. It's a RPR. There's a prismatic joint there, right? So we know very quickly this is 0, right? If you see, we don't have P02, but we really don't need it. This is the prismatic joint. There's no contribution to J omega. Now, how do I find this? This is the axis of the first joint. I have P01. You go here and read this. This is the axis of that rotation matrix, right? That's the Z axis. So that's your Z1. This is your Z3. It's the same thing, right? You have transformation, the transformation matrix. The third column in the rotation is your Z3. Z3. This is going to be negative sine 1, cosine 1, 0. That's your J omega. So this is how you find Jacobian from the transformation matrix if you have them. Now to find G, what is this doing now? To find JV, I'm gonna write the equation for you here so you can think about it. So we will say, sorry, we say that JV is going to be partial of PE with respect to theta 1, partial differential of PE with respect to D2, partial differential of PE with respect to theta 3. Okay, so your J, what is your J? Partial of PE. I'm gonna write this. You can follow this equation forever whenever you are dealing with these problems. And then Z1, Z2, and this one, sorry. This one was 0, this one was your Z3. I'm going to divide this so you can see what's happening here. This is 3 by 3, so 3 by 3, 3 by 3, 3 by, so this part is 3 by 3, right? The lower part. The top part is going to be also 3 by 3. Now I brought the top part down here so we can calculate it separately. Now, how do we do this? How do we find PE to get the partial differential, the partial derivative of that respective joint variables? Do I have enough information to find what is the position of end effector? Raise your hand if you think the answer is no. All right, so how do I find PE?
Pick the first column of P 0 E
Yes,
and then get through it.
so this, well, let me use just, so this guy is the position of your end effector, right? Now you have, so this PE basically is PX, PY, PZ, right? Yeah, and right here. So PE is PX, PY, PZ. So 3 subfunctions, you have 3 variable. You're just basically getting the direct equivalent for that, right? So PE, PX, PY, PZ with respect to theta 1. PX, PY, PZ with respect to theta 2. And same for that one, it's going to be 3 by 3. You put them on top of each other, you have a Jacobian. So this is, if you have the transformation matrix, this is the quickest way. Now, this might give you ideas, you know what, I'm gonna calculate transformation matrices and find Jacobian. Cool, that's a good way. Sometimes you say, and you know why, I can, if you have the diagram, I can find the distances, p's, from the diagram. I'm gonna use the other method I saw. Use that. Either method works, whichever you choose. They should give you the same solution. Really depend on what you have ready at hand. So for your code, like for PA2, depending on which method you chose, POE or DH table, you might have a different way of calculating Jacobian, but it should give you the same solution. This is a long calculation. I'm just going to do it for one part, but in the annotated version, I have all of it. So JV, so PX is L1 cosine 1 plus L2 cosine 1 cosine 3 minus sine 1 D2 with respect to our first variable theta 1. Then I can be lazy and say D2 and then case theta 3. So for here, you write D2 for PY. And then continue, this is PC. All right. So the annotated version has all of it. Did I do it wrong? Yes, yes. I meant don't say it. I know. Okay. I already know what I did. Okay, let's just write the whole thing. L1 sine 1 plus L2 sine 1 C3 plus C1 D2. So this is the second subfunction with respect to D2. Then third is negative L2 S3 respect to theta 3. Now copy over, just change the variable. Do it wrong again. Theta 1. Sorry, theta 1, and then this is going to be D2, D2, D2. Same things, and then same things. Theta 3, theta 3, theta 3. Yeah. All we have to do is to put them on top of each other. Now you'll see that I would probably not ask you to create this from beginning in exam or anything because it takes forever, but if it was an assignment homework, you could use MATLAB, right? You just find it, you just calculate that. Especially if I gave you like values to find at this many degrees. So you have to find this and then plug the values in there. So you kind of have to guess what kind of questions, like we have midterm 2 coming, right? So you have to guess what kind of question you will get. So this wouldn't be something that I will ask you to do from scratch, but it might be, hey, you have this transformation matrices, now give me Jacobian, something like what I just saw. Or a very simple robot like RR or RP that is very quick. All right. Okay, so time almost there. So for kinematic singularity, so I put it, I posted annotated version for last class. I added like just handwriting everything, so I just type it because my handwriting are not the best. So problem solve for this class. So singularity happens when locally your robot loses ability to move about or along a direction, right? So you could mathematically find it using determinant of your Jacobian becomes 0. Now, when you have determinant of a matrix becomes 0 and you want to find out what is the first question to ask yourself before you're going to be trying to solve it. Or, there. Maybe my question is not very clear. So let's say you have a matrix called A. Okay, I want to find if the determinant of this is 0 or not. Before doing that, what should I do? What should I check? What does it mean? So let's put it in simple words. You want a matrix, a square matrix, right? So it has to be n by n. If it's not, Jacobian happens to be not. You have seen 6 by 3, 6 by 2. Usually it's not square. So if it's not a square, it's not invertible, or you cannot find the determinant of that to be 0 because the singularity has to be invertible. So what do we do? Make our life easy for ourselves. That's basically, we will reduce it only to the element that we have value for them. So this, there's a bunch of zeros missing here. 0, 0. So this is your J omega JV. This is for RR robot. So we will reduce it to the ones that they had element in there. Now it's 2 by 2. Reduce it to something that we can find the determinant, right? Then find the determinant equal to 0. Check if that makes sense. That's going to be your singularity. Because we reduce the Jacobian matrix to something that we can find the determinant, right? So now you have to look, check if this makes sense. So here for that example, when your theta 2 is 180 degrees, the arm is folded, right? So this arm is folded to the first one, so you cannot track if L2 and L1 are equal. That was the case for your CP12. End of L2 will be at this center, and you cannot track, and you're basically losing that arm, right? So that will become the singularity. But that's something that you have to look back at your robot, see if it's still the case. So you can't just follow like, okay, find the determinant. There are 3 solutions, all of them are singularity. You have to do a little bit of more work if you are using the weakness matrix. Usually I like to follow a like visual plus the math to find the singularities. So CP14 is due the beginning of next class. The goal is for you to try to use the explicit method. If you don't finish it, it's fine. I want you to go through today's lecture and try to create J omega and JB separately from the explicit method, right? So this will be completion based. You can also use the implicit method. So you can solve in 2 ways. But my goal is mostly for you try to use one of the method, or if you could do explicit, it would be great. So you either use the implicit method, which is J becomes P13, P23, and then the last one. So basically finding the end effector from frame 1, frame 2, and then you're at that last frame. Then this one is, I'm gonna just write J omega so you can try to find J omega yourself. So either use implicit or the explicit method, which J is partial of PE respect to theta 1, partial of PE respect to theta 2, and PE respect to D3 and J omega. We said J omega is similar for both of them. Well, both of them will be similar, but we know J omega is only because of revolution, so that doesn't require much of calculation. So either of these, if you can find yourself with both of them, would be great. If not, try this one first, because that should be easy. Okay, so since we are going to autumn break, I'm not giving you anything that is long. Work on your homework PA2. And these are your graded exams. So A to J here. I'm going to do this here. That's K to R.